the work done by a force on a body happens to be an aspect of energy of the body. So according to the work kinetic energy theorem, the work done, the mechanical work done by all the forces of this universe that are acting on that particular body. So the net work done you can say, total work done, net work done results in the change of kinetic energy of the body. So this is final kinetic energy minus initial kinetic energy. Net work done by all the forces is equal to final kinetic energy minus initial kinetic energy. So this is equal to delta KE. So this delta KE is pertaining to the system. If there are more than one bodies involved, then we have to find the change in kinetic energy of each of the bodies. That is what we mean when we say that this delta KE is of the system. So let's understand what this statement is saying. So let us say if there is a body kept over here and that body is resting on a horizontal surface. Let's analyze the forces that are acting on this body. So this is the normal reaction force. This is gravity, mg. Let us say this force F is acting at an angle theta. Let us say all these forces cause the displacement of the body as shown. Because of this, there is going to be change in kinetic energy of the body. So work done by all the forces, so work done by normal reaction here happens to be 0 because displacement is perpendicular to normal reaction. So while taking dot product, n dot displacement is going to be 0. Similarly with mg, similarly with the f sin theta component of force F. So the only component that is going to do work is f cos theta. Let us say the magnitude of this displacement happens to be x. So f cos theta x is the work done by the force F, or it's rather also the net work done on this body because no other force is doing work. There is no friction involved. So this is going to be equal to the change in kinetic energy. Let us assume that the body was at rest initially. So the final kinetic energy of the body happens to be half m vf square. The initial kinetic energy of the body is 0. So minus 0. This is how we write down the expression for the work energy theorem. So this is an example. Let us understand this using another example. Let us say a body is falling under gravity. Let's say a body is falling under gravity and there is a force of air drag involved. So the force of gravity happens to be mg and the force of air drag is assumed to be a constant force F subscript d. F subscript d is the force of air drag. So let us say under such a condition the body moves in the vertical line by displacement h. Okay, so the net work done on the body can be said to be mg into plus h, because mg happens to be acting in the direction of displacement. So cos theta is going to be 1 because theta will be 0, minus fd into h, because here the angle between fd and displacement is 180 degrees. So cos 180 is going to be negative 1. So this is the net work done. So this net work done happens to be equal to change in kinetic energy. Let us assume that the body initially was at rest, so it is released from rest, u is equal to 0 initially. So when it reaches this point, it would have some velocity v. So this is equal to half m v square minus half m 0 square, which happens to be 0. So this is how we can write down the expression for the work kinetic energy theorem in this particular case.